right, so there's not much actual notes that go here, but I kind of want to tie it in from Friday with how we decided Fridays, how we decided today. So Friday we had a chi-square test. What was one of them called? What was the very first one called? When did we use a chi-square test for independence? When did we use a chi-square test for independence? There was one sample, one population, and then what did we do? What did we actually record? How many things? So the easy way to think about this is one sample, two variables from each. Our other one from Friday, or Thursday, whichever day it was a chi-square test, what? Homogeneity. This one we had two possible scenarios. So my kind of opposite here, opposite of this one would be what? Two samples or populations. Or two samples from two populations. And we record what? How many? One variable from each. But our other way to do this that doesn't look like one of those two is if we do a what and do what? What's our other one?
Are we writing this as 3 or 2?
No, this is the other way that this works. This is a specific one. Like, back to chapter 4. We're not doing one of these. We're doing a what? And when we do an experiment, what do we do to them? Randomly assign. So either way, we end up with a 2x2 table, a 2A table, not 2x2, it could be more than that. We end up with a 2A table, so we have two variables, and the math of any of those three scenarios ends up the exact same. So today, we're taking a step back and going even easier. The one from today is called a chi-square goodness of fit test. So that's our GOF that we saw in the calculator on Friday. Here we use, when we just take one variable with multiple categories or options. We have dealt with a lot of things that are, if we have one variable, it can only have two outcomes, which means it's binomial. Or if it has more than two outcomes, we have to reduce it to two outcomes. It is or it isn't. This is where we can actually have more than two outcomes, and we can finally deal with that for the first time. The number of each grade level in a school, the different percents that it represents. That's the type of thing that we would be dealing with here. So it's only one variable, and we're counting the number in each category. So when conducting a chi-square goodness of fit test, sometimes the problem actually gives you percentages for each of the different categories to use as our claimed value, or null hypothesis. So like, I think it's supposed to be 20% this, 30% this, so forth. Other times, you are just testing to see if the percentage for each category is what you think is going to go there. Sometimes I'm going to tell you what percent each one should be. Other times, it would make more sense just to see if the percentage from each category is going to be what? Equal. And because I don't always do an example from that, sometimes people get thrown off by that, but that should not be hard, so I'm adding this last sentence. So to determine expected counts, it automatic capitalized for me there. If I know how many total students there are, how do I know what my expected count would be for each grade level? So say there, I don't know how many students are here. I mean, it's like over 17 now. It's like 1,700 students. If I thought that there are an equal number of each grade level, which there aren't, then how would I figure out how many I would expect to be in each grade level? You just what? Multiply by a quarter, or if I did it this way, I would just divide, which is the same thing. Divide the total number, and I'm right, total number of trials. Individuals, trials, whichever way you want to say it. Which is the same thing you're saying. I would divide that by what? By the number of categories. And then it would be the same for all categories.